Yay, that might be the live stream that goes on air as much on time as any of the previous sessions. Good to know. Okay, one without feedback, so that goes back to me, I guess. I'll check it after the lecture. Oh, no, I forgot it at home. I wanted to bring you a physical printed copy of Communications of the ACM because it's an actual magazine, but yeah, left it at home. Next time, maybe. It's like the member magazine of the ACM, right? But they also have some research articles in there, as you have seen. Is the group somehow getting smaller that's attending live? It's definitely not 24, so maybe you're all isolating at home. Fine by me. I mean, it's lovely to have a live audience too. Well, I'll take what I get. Okay, I think time to start. Now, I didn't prepare any specific announcements. Let's see. So the video presentation should be mostly settled. I'll check the remaining articles after the lecture. If you had a look at the bamboo cutting problem and stumble across anything that's not clear, maybe just raise that on Campus Wire. We might discuss this a little closer to the deadline. I think for now, just read through it and see if you understand what it's about. Yeah, there's a second class test that some of you have already submitted. For the class test now, class test 2, I already marked the grades as posted right when I published it. So it should be when you submit your answer, you should immediately see your marks. Please pay attention to the exact format, especially for this one. If you type the answer with spaces, it will not accept it. And I can manually overwrite this, but I feel reluctant to do it 50 times. So please do the practice tests to see if the format is the right one. And then you can avoid the extra hassle. Yeah, and I'll see if I can put out a new class test soon. I think these are short and small, so I hope they don't add to the massive load of deadlines that you guys have, and instead give you a checkpoint to stay on track with rehearsing a little bit before everything comes down to you towards the end when we approach the exam. I think that's all that's going on at the moment. I hope I didn't forget anything. Yeah. Anything else? Talk about continuous assessment, the class tests, videos. Well, you remind me if there's something else. All right, then welcome back to COMP526 another time. A new unit, fresh topic, even though quite related to the previous unit. We'll still talk about string matching, but this time how to do this in parallel. And this will be a relatively short unit. It just gives you another kind of flavor of string matching and a new perspective on it. And will turn out to be a second somewhat illustrative problem to see how parallel algorithms work for this. Okay, without further ado, what we'll do is see some parallelization strategies that indeed work for a whole class of fairly simple problems. And we'll identify what cannot possibly be sped up further in some cases. So again, these two things are going beyond just string matching, but it's a nice way to illustrate them. And then there's a concrete new method that you haven't seen. There's another string matching method, which is particularly suited for parallel execution. So we have seen quite a few string matching methods in Unit 4. And they were more or less efficient, apart from the brute force method. But all except the brute force method really gained their efficiency from building on the knowledge of the previous guess. Right? The brute force method was kind of oblivious. For each position in the text, it started from scratch. But all the others, what we were doing in many different ways was trying to gain advantage from what we've already learned in the previous position and take that knowledge to the next position in some way or another, sliding forth and back and all these things. Now, if you think about string matching from a parallel perspective, this sounds exactly like Poison. What we need for parallelization is that things are data independent, that the next computational step does not depend on the data or the result of the previous computational step. And here we did exactly the opposite. So it seems like for parallel string matching, the sequential methods are worse than what we had before. Okay, someone posted on Campus Wire, is the live stream working fine? Okay, the app is a bit slow. I'll continue with the parallelized string matching in a second. Looks like it's sorted for now. If not, you can still use the Slido Q&A if you want. All right, back to string matching. It looks like all the effort we spend on making the sequential methods faster is to the detriment of parallelizability. And so it looks like we might need new ideas for turning this into parallel. I want to take one modification to the problem, just because from a parallel perspective, this is much more natural. String matching in this unit will mean we want to find all occurrences of the pattern in the text. Just if you think about it, finding the first occurrence would necessarily mean some synchronization step after the parallelizing, in parallel finding all the occurrences. And then it's just an additional step after this. So it's kind of more natural to stay with all the occurrences. And if you want, you can still find the first afterwards. But it seems in parallel not to make much, there's not much you can gain from the fact that you want to find just one. Whereas in sequential, it was kind of natural to stop at the first. We'll also assume that the pattern is shorter than the text as before. Otherwise, you don't have to do much. I want to look first at some elementary tricks, and this is the part that goes beyond string matching. It's something that we haven't talked about in the sorting chapter because we were deeply buried into getting sorting methods fast. But in a way, let's start rethinking parallelization from scratch and try to find what is easily doable. And so there's this notion of an embarrassingly parallel problem. Slightly cute term that just means it's a problem that's so easy to parallelize, you shouldn't even be very proud of doing it. It's embarrassingly parallel. It's very easy to break into many small subtasks, and they can all be solved independently of each other. I left the definition deliberately vague. There's no quantitative notions in there because I think the term is more of an idea or an abstract concept than a concrete mathematical definition. But a typical example could be the sum of two matrices. So you have two matrices with floating point numbers. You want to add them up. Well, how does that work with matrices? In the outcome, every entry is just the sum of the two corresponding entries. So you could assign one processor, at least on the conceptual level, to each outcome element, and it just gets the two elements from the input matrices and adds them up. That's n squared, if n is the size of the matrix, say it's a square matrix, n squared little tasks, and they're all independent, right? That's embarrassingly parallel in its essence. Then matrix multiplication is somewhere in between, right? The individual tasks, there's some potential overlap, but it's still independent enough. It's overall a little more effort, but you can still, in a sense, independently compute each of the outputs if you want it. And if you can do this, that's the best case for parallelization, because remember Brent's principle, you can, in a sense, just schedule all those little tasks on the processor you really have, one after the other. The other problem we've seen and looked at from the parallel perspective, sorting, is actually not embarrassingly parallel. It's not really clear how in sorting you would break the whole task of sorting the entire list into small little tasks that are independent. But if you look at our algorithms that we designed, there are subtasks that are of this type. For example, the partitioning step in quicksort, where we compare all elements with the pivot element. That's a task that every element's outcome compared to the pivot is independent of the others. So you can do this completely in parallel, and that's exactly what we did. Now, an interesting question is, how about our about our string matching problem? Is this embarrassingly parallel? That was, sorry, wrong direction. And for this question, I haven't really told you enough, or we haven't covered this yet. So there's no way you can know other than your intuition, or maybe you have seen it before. But I want to ask this question now and later compare and ask it again. Just what do you think? What's true for the string matching problem? We had 30 votes for the last question, and we're at 30 now. Well, 31 indeed. Okay, 3, 2, 1, and let me lock this one. So you see the results are different. Okay, can show you the correct one here and then switch back to this one. Let's discuss what's correct later after I told you. What could be subproblems in string matching? A natural candidate is to take each of the guesses as one subproblem. If you think about it, we want to find all occurrences. Every position in the text could be the start of an occurrence. So we could say each guess is one subproblem, and the task of this subproblem is to check if the guess is a match. Now that's great because these are indeed independent, right? I can try to take advantage of learning from what the outcome was in one guess and apply that to another one, but I don't have to. They're in essence, they're independent. And so I could do all guesses in parallel. And that's not the crappiest way to do it. Let's put it this way. It's also not the final answer, but let's first see what we can do. If you assign each guess one processor, and that just sequentially checks for all the characters, in the worst case, it has to check m characters if these are all matches or all near matches. So you would need m time, parallel time for the matches. And you would need as many processors as there are guesses, so n minus m, right? And that's what's down here. So the work is n minus m, the number of guesses, times m. And that's the same across these other ideas. It's just the parallel time that we can slightly improve. And here it actually depends on the details of the machine. So you should have seen the parallel AND in the tutorials, or you're doing this week. But I think you've seen this last week, haven't you? Okay, some nods, some defiantly denying. So you can look this up. The connection here is checking whether a guess is a match is really checking if all these characters match. And then it's a match if and only if all the characters match. So that's a big AND. Is this equal? And is this equal? And is this equal? And is this equal? So after the character comparisons, it's the same problem as computing AND of an array in parallel, all the bitwise AND of all the bits in a bit array. And you've seen how to do this in log m time on a crew RAM, and in constant time if you can actually do concurrent writes. And you can even have this strict version of conflict resolutions. So that's all neat. So the parallel time is really good. It's constant. It's the best you could hope for. But remember, again, Brent's principle, you don't usually have as many processes as the text is long. So you also have to take the work into account. And this is essentially n times m as the brute force method. So we know there are better sequential methods. This method will not be work efficient. All right? So what can we do? We can be slightly smarter by saying, let's try to take advantage of the fast sequential methods that we have. And so a way you can do this here is you divide the text into blocks. And it's important that these are not just m long, but 2m. You will see that they're overlapping. So say these are length m. And then the first block is this part. The second block would be this string. And then the third part, this string, and so forth. And now you're finding inside of each of the blocks, you use a fast sequential algorithm. So you use a sequential method like KMP, say, inside each of the blocks to find all the matches of the pattern inside the block. Now, the time for this will be essentially linear in m, because both this snippet of the text and the pattern are length m, up to some constant factors. So you need that in parallel time. Now, have you found all the matches by doing this? So suppose there is a match somewhere in the text, say here. That's our pattern. It won't be found in the first red one because it only contains a prefix of p. It won't be found in the third, but there's this second that overlaps, and then we know that this occurrence is fully within this red segment, so it will be found in the second block. If an occurrence is exactly aligned with one of these blocks, it'll be found twice. If you want, you can try to be smart and avoid that case by checking the outcomes, I guess is the easiest. It will only be reported in 2 blocks, in this and in this. So it might be enough to just avoid that. I wonder if it's enough to just make the blocks 2m-1 long, and then we don't have the problem. Then you don't catch all overlaps, potentially. That's a detail that you can solve either way. Either filter out the duplicates or try to avoid them up front. What we achieve with this simple method is parallel time m. That's as here, but we've seen you can do better. The positive side is the work is efficient because this comes down to n times m, to n divided m times m. That's the number of blocks, right? N divided by m, with a factor of 2 that is omitted in the theta. And each of the blocks takes m work, so the total work is linear in n. Remember, we used to write theta n plus m for the sequential methods, but with the assumption that m is at most n, we know that is the same as linear in n. So why did we obsess with writing this like that in the previous unit? The thing is that if you pre-process the pattern, you might apply the same pre-processed pattern to several texts, and then maybe you don't know at the time of pre-processing the pattern how long the text will be. So you might already have spent the time linear in m, and then you discover, oh, the text that someone's giving you is actually shorter, and you wouldn't have had to do anything, but it's already done. That's why in the last unit, I was a bit more careful and said, in general, whatever n and m are, the time will be n plus m. Here, I'm a bit more sloppy and say, let's only look at the case we're given the text and the pattern at the same time. And if the pattern is longer than the text, we don't bother to do anything. And we have a way to check the length in somehow without iterating through the pattern. And the only interesting case is when the pattern is shorter than the text. And then these are the same. So that last part is a work-efficient method, but it's not perfect in terms of the parallel time, right? And so if I were to ask you the same question again, I'll open a fresh copy so you can see, you can change your vote and we can keep the old result. I'll wait till we have 30, even though the picture is fairly clear now. Okay. If you were quick last time, you would have seen this answer anyway. So why is it, in this sense, embarrassingly parallel only if the text is much, much longer than the pattern? In that case, you can use this second method and break the text into these blocks of length 2m, and can use a work-efficient method and still have an efficient parallelized method, fairly efficient. Whereas if the pattern and the text are roughly the same length, there's not so much you can do. Even these more fancy methods, they look like the parallel time is decent, but then the work is so big, so unless you have many processors, you won't really have much of an advantage. And for this work-efficient method down here, if the pattern and the text are roughly the same length, it doesn't really do anything. It falls back to the sequential method. All right, so let's wrap up what we've seen so far. The elementary methods are simple, and that's always useful. It's always a good thing to have. We could even run them not on a shared memory machine, but on a distributed machine where, well, on a distributed compute cluster or something like this, where each compute node only has a portion of the text. Because the problem is local in the sense you only need a segment of the text that's roughly as long as the pattern. You could still do this, and these simple methods would nicely work with that. But we only really get a speed up if the pattern is quite short. Now, what would we like to improve upon this? What can we do on top of that? It would be nice to have work-efficient methods, but then improve the parallel time, so we get better speed up. And the only way to get that is to get at the matching part. somehow we have to parallelize the matching process. The idea of breaking the text into little chunks of roughly size m, that looks useful, but unless we parallelize that step as well, we will be stuck with parallel time m. So it looks like we need some new ideas, at least with just black box puzzling together either the brute force method or existing sequential methods. We won't break this m time barrier. And that's what we'll look at next. I'll briefly check again if there's... Okay. No other messages on Campus Wire indicating further problems, so let's suppose this worked. I think the audio is fine too. Well, you would let me know if not. All right. Then let's continue with this one straight away. In the next subsection, I want to introduce a notion on strings that at first seems unrelated to our task, but it will be the key ingredient to a different way of string matching that then is more useful for parallel execution. And that's periodicity. So let's first start with the definition, and I'll walk you through the example then. If we're given a string, as always, and characters, then we say it has a period p, so p is a number, and it has a period p if for all positions, if you start at the ith position and you add p, you find the same character. All right. There's some boring consequences. P equals 0 is always a period, but none that tells us anything. And any number bigger than n is a period, just because then this for all statement is empty. This iterates over all numbers in this range, and if that range is empty, it's an empty statement. So again, these are technically fulfilling the definition, but we'll not really regard them as periods. They're trivial periods if you want. So we'll exclude those from the discussion. But strings can have non-trivial periods. And here's an example. So if you take this string written down here, and you take a copy of that, shift it over by 6 positions. So you match position 0, right? So let me maybe write down the indices just once. I know this is baby example. And up here as well. Then you see you match position 0 with position 6. That's a shift of 6. And if you do that, all the characters match up. And that's the condition that we need for a period. There's another string that has a smaller period. And so you see a small period means there's a lot of repetitiveness going on in the string. And in particular, we'll come back to this, but if this period is bigger than half of the string, then as in this picture, you have some overlap between prefix and suffix, but that's about it. If the period is substantially smaller, then you see there's a certain range, this ABA, that repeats over and over in this string. And we'll use this fact in a second. I want to connect this. If you've seen the picture on the previous slide, maybe this already sprang to your mind. We've seen something like this before, and indeed we have. So in other words, if you have a period and this p is the shortest, is the smallest number p that is a period apart from p equals 0, then this is also, if you take the first n minus p characters, that's the longest prefix that is also a suffix of this string. So I guess we want to have the picture for this. If the minimal period is p, then that means if you take the first so and so many characters, they're down here, n minus p, that is also a suffix of this part. Okay, so this string here is our S0 up to n minus p. And this here is the suffix starting at p. Okay, sorry, should be a little clearer because the square brackets are different. I guess I should have said here these are equal, right? What's also true is that the longest prefix that's also a suffix of s has length n minus p. And that's something I told you in the last unit. Please memorize. You remember the red box? That's exactly the failure function of the COMP algorithm. So in short, the statement here is, if a string has a minimal period p, then you can get this p from the last entry in the failure function. It's the failure link of the last state in the automaton. Okay? Just because if you had matched the entire pattern and you now find something you want to continue, you have to shift this over exactly as much as the period is. A second small observation about periods is this lemma. If you have a string that has two different periods, p and q, and they're not too large, so their sum is less than n, then you also have a period for the greatest common divisor of the two. And for that, I just want to give you a proof by example. Now, this is not in general a valid proof. And the formal proof used to be part of the tutorials, but it was never really very insightful, and we're not using the lemma massively. That is. Okay, this is not working. Let's do it this way. So let me see. Might have made this a bit short. Let's do a small example. So let's suppose the string has period. It's boring. Let me make the example a little bigger. Otherwise, we don't see the interesting part of the statement. I want to have two numbers whose greatest common denominator divisor is not just 1, but also I need them to be in sum less than n. So the example has to be a little bigger. So let's take a period of 6. And so the implication here is these are all the same. Right? And suppose we have another one. So I'll just put this in the same as the other one. Let's say we also have a period of 4. Which first of all just means that these are the same. But of course, equality is transitive, so it's also these are the same. And so let's suppose we put an arbitrary letter in the first position. Say this is an A. Now, if that's an A, of course, this is the same A. And so by these equalities, it immediately implies that this is an A and this is an A. And look what happened. So if you put this A in the fourth position into this one, then you get an A here. So A also must be at the second position. And so you see, you can fill, with these games, you can fill every other letter, which means that the string actually has a period too. So you can do the same if you put an arbitrary letter in the second position. It is inherited here and here, but also here because it's also the second position, so it gets into here and here. So that means it goes into the fourth position. So after fixing the two letters, the first two, the equality, as I said, this is not a proper proof of this statement because it's only shown on this example. But that's the essence of what's happening, and I don't think the formal proof in this case is really insightful. So now, after introducing this idea of periods and the idea of shortest periods, and the previous lemma is just a cute way of finding the shortest period. You can try to look at the string and guess what periods you find. And if you found two, you can always jump to their greatest common divisor and get a smaller period, potentially. So that's a way to find periods by hand. The important notion here now is that of a periodic string. And we call the string periodic if its smallest period is less than half of the string. And remember, that means you shift the string over by less than half of it. That means it has to repeat at least another time. Maybe repeat the little picture again, just conceptually. So suppose the period is like this. Then that breaks the string into these blocks. This must be the same as this because it's the same string. Oh, come on. And then because of equality, you have the same block here, and that copies to here. So the string consists of the same block repeated until at some point it stops in the middle of a repetition. And so we can say this is a case where S is highly repetitive. The more precise statement is stated here. S is determined by some smaller string of length p, and you keep repeating this until you filled enough characters. And the other case is an aperiodic string. And in a sense, the periodic strings, they're kind of redundant in that they are not really n characters worth. They're determined by much fewer characters. But the aperiodic strings cannot be written in this way. And so the formal definition is shortest period is bigger than n half. All right. Time to wake up and see if this notion is clear enough. So here's a string for you. Is that one periodic or not? Okay, 24. We get up to 30. Yeah, a couple of people still typing. All right, seems all done. I wanted to click on log. All right, in this case, it's not periodic, which might be surprising. The thing is, this string definitely looks boring, right? It has lots of repetition, but it's not periodic according to the definition we've just seen. And the reason is that if you take this string, many A's, but then a b at the end. There's no way you can overlap this with itself without creating this. Okay, I didn't switch the, thanks. So correct answer is no, as I said. The reason is that whenever you shift the string by any amount over to the try to overlap with itself, you will always place the b atop of an a. So you can never have this match. So what's the period, the shortest period of this string? It seems any p doesn't work, but there is always a shortest period, which is n. If you shift the string entirely behind itself, then by definition it's a match because there's nothing to align anymore. So shortest period is n, which is definitely bigger than n-half, and so it's aperiodic. So don't be tricked into thinking that periodic necessarily means repetitive and vice versa. It's not exactly the same. And indeed, this is a fairly restrictive and concrete notion, this periodic. All right. I think it's good point for our little break. Shall we take 5 minutes? So just a short one, then we'll see how we can put this to good use in string matching. What do you guys think of the break? Is it useful or is it a waste of time? I wanted to ask this on Slido, right? When we started again, I thought I'd need the break. But then once we left it out and I survived, so I guess I would vote don't care. Well, that's the length of the blocks. So that's n if you want, right? So we're using KMP, which normally has time n plus m. And what is n in our case? We apply it to one of these blocks, and there are 2 m characters long.
Because we use KMP, so we have to.
Well, what are we doing in this step? In parallel, for each of the blocks, we call the KMP algorithm, say. It says some efficient sequential method, but we might say concretely the KMP algorithm. And that has running time n plus m, but n here is the length of the block. So that's 2m. Looks like the vast majority seems to like the break as it is. I didn't put an option. I want a shorter break than 5 minutes because probably 5 minutes is already the shortest that makes sense to at least go to the restroom. All right, 47 on my watch. Everyone ready to continue? A cheerful yes. I guess you won't get more ready, so you might as well. In the next subsection of this unit, we'll put these two things together, the ideas from simple methods of how to parallelize string matching and this new concept of periodicity of strings. And it will lead to something that's called string matching by duals. If that doesn't sound exciting, I don't know what. Let's see where that comes from. Another little consequence of having a period is that you can align the strings on top of each other, and if you don't have a period, there must be a reason why you don't have one. So let's assume that we have a given pattern that does not have a certain period p. Then that means there must be a witness position that shows us why there can't be this period p, right? And well, it's denoted by omega here, little omega. So it's just a position in the pattern where if you shift it over by p positions, you have a mismatch. That position then witnesses against the periodicity, against the period p, right? Is it clear? Like when I have a non-period p, some number that is not a period of the string, there must be some position where there is a mismatch. Otherwise, it would be a period. So in pictures, if I shift this over by p and it's not a period, well, there must be one position here. If these are all matches, there must be one position where the two characters are not the same. Up here and there. Otherwise, it would be a period. And so then this position is our omega. This is omega plus p. Okay? That's a fairly simple concept, but it's quite interesting and useful because it allows you to exclude guesses. And here's how. If you have a pattern that does not have a certain period p, then whenever you have two positions in the text that are p apart, only one of them can be a match. Maybe none of them is a match, but they cannot both be a match, simply because that would mean a contradiction according to the witness. So suppose both were a match, then we would have the position starting at the second occurrence, and omega positions into the pattern. So that would be the same as p of, so that's the position in the text, and that would be the corresponding position in the pattern. But this is not the same as the position p shifted by the witness definition. But this again would have to be the position in the text that's using the same equality here. It's just using the second match. And these two are the same, so, right? The parenthesis doesn't matter. So these are not equal according to that. And that's a contradiction because, I mean, it's the same position in the text. So again, if we have a non-period p, out of any two positions that are p apart in the text, I and I plus p, only one can be a match, or maybe none. Another simple observation, but again, useful because now we can do something that's called a dual between those two positions. We can take those two positions and say by checking the position for the witness character against the text, I will either find a match with one or with the other characters. So there's the two characters in the pattern, the one at the witness position and the one p shifted. And the text can at most be one of the two, right? So that's, again, spelled out what's in the inequality above. And so the other can't be a match, so it can be excluded. That's how we can get rid of guesses. All right. Let's see an example. Note here that P is aperiodic. That's not exactly spelled right. That's slightly better. We will discuss this algorithm only for aperiodic strings. And the periodic strings, because they can essentially be reduced to their the repeating part, they can be handled somewhat similar, but we won't discuss all the details here. It's just the high-level idea again. But the example for now works fine with this string because it is aperiodic. And let's first compute the so-called witness table, which is for all non-periods, what is a witness against this periodicity. And you can feel this intuitively, like it's not the efficient way to compute it, but it's the manual way to see what's happening. If we shift by 1, then we could potentially have period 1, but well, we don't have period 1 because there's a mismatch at this position. So there's a witness against period 1, namely the index 0 in the pattern. That's this index, and if you shift by 1, you find a mismatch with the character at I plus p. 0 plus p is 1, so that's what we compare with here. Okay? So two things. The string does not have period 1, and we have a witness for that non-period. If we shift by 1 more, the string could have had period 2, but actually it doesn't, because at this position you find a witness against this period. Again, the top number is the one that we take in the witness table, and if you add 2, you get to a different character in the pattern. I think the game becomes clear. We find the same for shift by 3. So these are different, so we put the 1 into the witness table. And even 4 doesn't work. We still find a witness against that. And 5 doesn't work either because of this C, right? It doesn't occur anywhere else. And that's it. If you check 6 is actually a period of the string. This is only one character matching, but at least not nothing. So the smallest period is 6. And we've proven that by just exhaustively checking all others and writing down the witness against them. And now let's play the dual if we have this text and we try to find the occurrences of the pattern in this text. Now I know there's only one C and you can already kind of guess manually where the occurrence could be, but that's not what we want. We go strictly by these duals. The first two is we can play position 0 against position 1. So guess I equals 0 against guess I equals 1. That means we have a potential period of 1, but we know it's a non-period, and we have a witness against it. So we check the position t equals 1 is a B, and that's not the position of, that's not the character of the pattern at omega at 0, which would be an A, right? So we cannot have an occurrence at 1. We might still have an occurrence at 0. We can't tell at this point. but we've excluded from checking the witness position in the pattern against the corresponding one in the text for the two potential matches, for the two guesses, that at least this one is excluded. Let's play position 0 against position 2. So remember, after this first round, 0 was still in the game. It could turn out to be a match from what we've learned so far. So we now play 0 against 2. Again, we have a witness against this periodicity, so we won't have a match at 0 and 2. And in this case, 2 says we check position 3. And if you compare the character at omega plus p with, come on. There you go. Let's show in the picture what's going on. So this is one potential match. This is the other potential match. Omega 3 means we're taking this character and this character. Sorry, we're taking the 3 and this one. 0, 1, 2, 3. So we take this one and okay, sorry, the pattern is longer. That's 2, 4, 7, 7. That's why I didn't overlap. So we take these two. We pick the character in the pattern here, which is the C, and it's not a B, so we can exclude the 0 this time, right? The character that's matched by this guess to that position in the text corresponds to a mismatch, so we can exclude the occurrence at 0. No occurrence at 0, potentially 1 at 2 still. So next one is we compare positions 2 and 3. So again, this one, 7 characters. This is surprisingly hard to do. Okay, our witness is at 0. So we take this one and this one. Now we find the occurrence in this one. In the further shifted pattern is an A, which doesn't match the B. So we can, from that dual, exclude the position 3. Okay, that's how you go through. It's a little tiresome in the example to check, but you always do just a constant number of character comparisons between pattern and text at these positions of omega plus p. And so after each dual, you can exclude at least one of the potential guesses. And so that brings us to the following algorithm, how you make use of this dualing process. And as I said before, for what I describe here, we'll assume the pattern is aperiodic, and we'll cover the periodic case only in passing by saying you can do it somehow similar. We first pick a block size, which is roughly half of the length of the pattern. We know that the pattern is aperiodic, so its smallest period is bigger than m half. And that means we can compute witnesses against all the periods up to this m half. Okay? So aperiodic means these exist. And then we look at blocks of the text of mu consecutive indices. So we block the text up, and this time non-overlapping. And in each of these blocks, we run duals to eliminate all but one guess. So why do we pick the block size like this? Because that's the potentially largest P for which we have a witness against that period. We only assume P is aperiodic. In the previous example, we had a pattern of length 7 and the shortest period was 6, so we could go further up. In general, if we just assume aperiodicity, we can only assume that there's a witness table up to m². That's why we have to choose the block size like this, a little more conservative. We run these duals as we've seen in the example. So out of each block, at most one guess can survive. All others are eliminated in one of the duals. And that means out of every block, we only have one guess left. So we can check all of those roughly n divided by m guesses naively and still stay in linear time the length of the text. Okay, that's the idea. This is all sequential for now. We haven't touched on parallelism yet. I want to briefly go through the individual steps to convince you that it's another worst-case linear time method. The first step is just computing one number. That's trivial. The second step, computing these witnesses, I'll comment on very briefly later, but it's essentially a twist on K and P. And if you've seen the connection between the shortest period and the failure function, maybe this is not so surprising that the two can be reduced to each other. The third step has n divided by m blocks, roughly. And we do m duals in each. So multiplying that out is linear, order n. And similar in the last step, we have n over m blocks, and at most one guess survives. Well, one guess survives from each block. And we have to check with m comparisons in each block, in each guess. That's another linear time, order n. So overall, we have another efficient string matching method. It has this blemish that, as stated, it only works for these aperiodic strings. That's why in the previous section I didn't include it, because it doesn't really have many advantages over the other methods, except for what's coming now. And the big advantage that it does have is it works in parallel. So this first step, I mean, all the steps basically stay the same, but we have to see how we can parallelize things. So the first step, there's nothing really to do. The second step is possible to parallelize, but it's very tricky. I will only tell you what is possible. And a reasonably complicated method gets it down from m to log m squared. But this part will be beyond the scope of the course. But what's nice to show is the other parts. So for each of these blocks, each block can be treated in parallel. They're embarrassingly parallel, right? They don't depend on each other, so that's great. And the duals can be laid out as a binary tree, like this. If you were to play the duals like in the example, always keep the surviving position and compete against the next free position you haven't tried, then the next dual would always depend on the outcome of the previous, and that's bad for parallelization. But if you lay them out like this, then these can all be independent. The bottom row can all play in parallel, and you don't need to know what was the winner of each to play the others. So like a tournament, and then you keep the winners playing against each other until in the final there's only one guess coming out as a potential match. And well, the parallel time is the height of the tree. We've seen this in Unit 3. So that's where this log mu comes from, rounded up to be precise. That's the number of duals, that's the number of duals that have dependency on each other. That's the parallel time. And for the last step, we can do one of the algorithms we've seen before in the first section. For example, the crew RAM that again does a binary tree to do the parallel AND. Yeah, unless this is maybe this is obvious to you, but this way of reordering binary operations into a binary tree, that's exactly what we did for the prefix sum problem in Unit 3. That was the first problem we really looked at for parallelization. And you see that this similar idea is resurfacing in many ways here. Right, so the matching part, what I mean by this is this one. The part that does all the duals and checks the surviving guesses, that's the matching part, and that can be done in log m time, parallel time, and linear work, order n work. So that's pretty much as good as possible. The only slightly more complicated step is this second one. So to compute the witnesses in a sequential algorithm, that is would have been in scope of the class, but since this is about parallel algorithms, I wasn't sure if that adds much to it. A similar algorithm to the computation of the KMP failure function can do this sequentially in theta m time. And the parallel algorithms, unfortunately, are much more complicated. And so I'll just state the results there, but we won't look into those. I want to finish that part and essentially string matching in the way we've seen it by briefly looking at what's known in theory, how quick you can do parallel string matching. If you use this most fancy, sophisticated way of computing the witnesses, you get an order log m time, parallel time, and work efficient string matching algorithm that can run on this crew RAM. That's pretty much the best you can do in this case. You can prove you can't really simplify or speed this up. If you allow concurrent writes, so again, this letter is the important part, you can do the matching part in constant time. This is not obvious for the duals, but it can be done. And we've shown that the last step can be done in constant time. That's the parallel AND. But it turns out the pre-processing, finding the witnesses, cannot be done in constant time. You still need this log m curious time for computing the witnesses, and you can't really improve upon this. But that's more, I mean, that's for your curiosity, say. As you've noticed, I haven't really told you anything about the details of these methods, so that's just more of an outlook. Okay. What you should keep is all the things about the embarrassingly parallel tricks. You can often get a work inefficient but parallelly fast algorithm by just doing all the tasks in parallel in a simple way. And then you can often get the work down by using blocks and using an efficient sequential algorithm inside the blocks. But to get beyond that, you often need problem-specific insight. But that's it. For many practical applications, it might be good enough to do a combination of blocking of the right size and some reasonable sequential algorithm inside the blocks. That brings me to the end of section of Unit 5, and pretty much the end of parallel processing for now. I want to start the next unit today. We'll just cover the motivation part, really. So this will be slightly more easygoing after this fairly technical and deep part. Okay, I didn't turn off. Okay, there was a question earlier. Sorry, I missed this one. Maybe we'll discuss this later. It's out of the context now anyways. Sorry, guys. All right. So one more time, new unit, new topic. Welcome back to COMP526 and a new unit again. This time on text indexing. So we stay in the realm of strings, and we stay in the realm of finding strings in longer strings. but this will be a slightly different approach. I subtitled it with searching whole genomes because that will be one of the main applications where this is in big use today. And since we just come out of this pandemic, or hopefully come out of this pandemic, you will all have done your PCR tests at one or the other occasion. And very much oversimplifying, what's happening there is you take a sample of some RNA from your body. RNA is this short-lived cousin of DNA that coronaviruses are also made out of. It's amplified so that you can see them, and then it's sequenced. So all of the occurring RNA is read off as a string. And then you try to find these strings in a database of known strings. And that's, well, the PCR tests use very specific snippets that are highly indicative of the specific coronavirus for COVID-19. But the method is fairly general. You can use this for many other diagnoses. And what's behind it in many cases is trying to find a specific string snippet in a huge library of known strings, of known RNA molecules or known genes from genomes, or finding a certain part in the human genome to know what it's doing. And this is very much the basic level of what's behind this is what we'll cover in this unit. I hope this makes it a little more relatable to you. When I did this last time, this was even more acute, but we'll still see the one or odd PCR test done at the time, one or twice. Of course, we didn't cover this yesterday. What do we want to achieve in this unit? I'd like you to take away from it a few notions that can be used to pre-process a large collection of text that doesn't change all the time, so we treat the text as static, so that we can work with the text. And these specifically are inverted indices and suffix trees and the modern versions of that. I want you to know what this generalized suffix tree is. Well, we'll cover that on Thursday probably. Again, as usual, it's not just about what is in principle doable, but how fast can we do it. That will make a major difference if you're working with gigabytes and more of data. And I'd like you to be able to design simple algorithms based on a suffix tree where you use what the suffix tree can give you. This will not make much sense at this stage where you don't know what these are, but we'll come to that. And same for the construction algorithms of these. There's a whole bunch of sections because I tried to break this up into many small parts as opposed to having two big sections. I would say this is my favorite unit because it shows some really elegant and nice results where some really famous people thought they're impossible, and I'll show you towards the end of the module all the details of how to do it. So it brings you quite close to the cutting edge of research, but every individual step is really quite fundamental and elementary to understand. It's just in quotes, that putting all those steps together builds something really fancy and complicated. I think it's a really beautiful topic, so I hope you can enjoy it a bit. It is a bit longer a unit than the other ones, so it will probably keep us busy for this and next week. Okay, let's have a look at what we're doing here, more formally than in the introduction. We'll look at what's called the text indexing problem, where we again try to find occurrences of a pattern in a text, but the game is different. The text is fixed this time around. So we get the text ahead of time, and well, I'll walk you through the examples down here in a second, what the text can be, but it's an abstract problem that's quite versatile. And we can pre-process this text, so we can spend some time on the text and make subsequent searches fast. The idea is that we expect many queries for different patterns, so this should be offset by the time we spend on looking at the text should be offset by those many searches. And if you want string matching, as we've looked at it in the previous 2 units, is more of an algorithm where you're given the input, you do it, and then you forget everything. And in this unit, we take more the data structures classes, the data structures lens, where you build the index of the text and you keep that around, and then you do queries on the data structure. Where would you find something that is text indexing at the bottom of it? Web search engines, in the simplest way, are like that. They do lots of other things these days. But when Google started, one of the basic functionalities was I type in a certain string and it finds all the websites where that occurs. And other sorts of search engines or inverted indices, well, we'll come to that in more detail. They still work pretty much like this. Dictionaries, in the classical sense of looking up words in a different language, they're pretty much static, but often you don't want to just find the keywords, but maybe also where this is used, and then you easily get to something like text indexing. Wikipedia is the same. I think the search function of Wikipedia is notoriously bad. I don't know what you feel, but it could sometimes work better. It often doesn't find occurrences in the text really well. It's basically looking at the titles mostly. Then slightly more esoteric, but I hinted at this. If you're working in bioinformatics, then you have these huge collections of known biological sequences. And a standard application there would be you take a sample somewhere from some deep sea area, you bring this up, and then you try to find what has lived there. And a way to do it is sequence these little remainders of life that you have in your test tube, and then search these little snippets in a big database of known DNA. And that way you can often, with high accuracy, identify what kind of creatures live there. And you can do all sorts of analysis based off that. And lastly, whenever you have text documents, any collection that doesn't grow too fast can be seen as a text indexing task. I want to look first at a conceptually very simple solution that is highly effective in some applications and is often the end of the story if you see text indexing in undergrad classes. So first of all, where does the word actually come from? It's something you find in books. So an inverted index is like the index in a book, where you have a list of keywords and it shows you where they occur in a book. And the same can be done, in a sense, for a whole text. So this often works well for natural language text. The big assumption that's behind this is that we only ever search for given keywords. So if you try to search for some word that occurs in a given book that you have, but it's not included in the index because the author thought it's not really relevant, you won't find it. Or a book won't list all the occurrences of "and" in the book. Just because people assume this is not interesting. So an inverted index in computer science is slightly extended from that restricted list because we can afford to have a little more space. You just take all the words that occur in the text. So can be just take the text and split it at white space. But often it involves some knowledge of the natural language that's used, so you often reduce words to their stem. But then at the end of the day, what it is a big map or a dictionary that maps from words to where they occur. And so I wanted to point out, so this is just a dictionary. Or one way to implement it would be a dictionary that maps from strings to lists of integers. So the keys are the words that occur in the text, and the values is the the list of starting indices, say, of occurrences. And you've seen data structures how to do this. Any suggestions? How would you do it if I give you a text file and you want to store an inverted index? Well, you could download Apache Lucene. It's a library to properly do it. A simple way would be just a binary search tree, right? It's a dictionary. The keys can be compared, so you could just have a binary search tree. The problem here is that it needs at least, let me write omega log n. It needs at least log n time to find something in this dictionary, and n is now the number of words, which could grow quite large. And this is even disregarding the fact that the comparison takes time. We're comparing strings and not just single characters. So it's just not quite as fast as we would like it. It would work, but remember, n could be something like all of the internet for a web search engine or all of Wikipedia. It wouldn't be great if whenever you type something, you had to wait some time that depends on the size of the data set. It's just not good enough in this application. What we really want is something that depends on the pattern that you search, because that's inevitable, but nothing else. All right, because we're running a little short, let me maybe finish after this one. So what's a try? Okay, I can wait a few more seconds, but it seems like we should spend some time on tries, right? In this case, let me not rush this last part, but I don't want to leave you with the cliffhanger, so I'll just tell you what a try is, and we'll look at it properly next time. A try is a tree data structure that stores strings as keys. So it can be used for a dictionary, but specifically for the case that the keys are strings. And it has some very useful features for this specific case. The term is a terrible name. It sounds like try. So if you put the plural, then tries as the pronunciation makes a little more sense. The rumor has it that it comes from retrieval, and so you should say tree, but tree is already taken, so we say try. I never really got this one, but it's common use, so I guess we'll just stick with it. Let's just look at the example here. What a try does is it stores the keys, the strings that are stored, as the labels on a route to leaf path. So if you take this path leading to this string, then you see if you read from the root A, B, A, B, and then this weird $sign, that's exactly what's in the leaf. So if a try stores a certain string, it will make sure that the path from the root to where the string is stored reads exactly as the string itself. And why is that a good idea? It means that, for example, all the strings that start with AB can be found as in the subtree of this node. They're all grouped by prefixes. And so this can be used for searching. If I wanted to know, does this try contain a string, I just start traversing at the root and follow down. And if I get stuck, it doesn't contain it. And if I find it, I found it. Okay, so search becomes quite simple. And well, we'll discuss the nitpicks here next time. You can also think about whether this already is good or not. And spoiler, the answer is not quite yet. But yeah, let's not rush this one because most of you haven't seen this before. All right. See you on Thursday.